All right, hello everyone. My name is Mrs. Bies, and I am one of the AP chemistry teachers at Riverview High School. This presentation is to simply go over some of the key concepts on the summer homework. This is a great study tool if you want to refresh your general or pre-IB chemistry knowledge before you go into AP chemistry in August. So we're going to go ahead and start off with scientific notation. So scientific notation is an efficient way to rewrite very large and very small numbers. If you have a very large number greater than 10, you're going to have a positive exponent when you convert it into scientific notation. If you have a very small number, less than 1, it's going to have a negative exponent when converted to scientific notation. Now, to get our exponent, you're going to have to move the decimal point until you get to a number between 1 and 10. Let's do some examples of that. So the first one, very simple, we're going to do 1600. Now remember, the decimal point would be at the end of this number, and if we wanted to move it to get to a number between 1 and 10, we'd have to move it 1, 2, 3 times to the left. Now, since this is a big number, greater than 10, we know we're going to have a positive exponent. So this scientific notation would be 1.6 times 10 to the third. Now, if we did this in opposition with, let's say, a very small number, 0.00016, and we wanted to convert it to scientific notation, we'd take that decimal point and move it until we got to a number between 1 and 10. In this case, it'd be 1, 2, 3, 4 times. However, since it is a very small number, that is going to be a negative 4. So now we will have 1.6 times 10 to the negative 4th for our scientific notation. Now, if we were going backwards from scientific notation to decimal or regular notation, we would have a number, let's say, 2.9 times 10 to the third, and 2.9 times 10 to the negative second. Now, these both have an initial same number, however, they are going to be different because of those exponents. So 2.9 times 10 to the third means that we have a larger number, right? Because if it's positive, it's going to be a big number. So we're going to be moving that decimal point to the right. So if we have 2.9 and we want to move that decimal point 3 times, 1, 2, 3, that means these will now become zeros, and this number is actually 2,900. Now, same thing goes with the negative 2, except in opposition. So we have 2.9 with a negative 2 exponent, so we're going to go 2 times to the left, which means our decimal point is now on the left side of those numbers. So our regular notation would be 0.029. Now let's do some practice for scientific notation. So it says convert the following to scientific notation. Our decimal point is here and we want to move it 1, 2, 3 times to the right in order to get it to a number between 1 and 10. So our integer would be 3.024. Since we moved it 3 times, it would be times 10 to the third. And do not forget your unit of grams. Now for the other one, we're going backwards. Remember, negative is going to be a small number. So since we want it to be a small number, less than 1, we're going to have to move the decimal point to the left. So if we have 3.99 and we know it's negative 6, we're going to have to move it 6 times to the left. So 1, 2, 3, 4, 5, 6. Now this is where our new decimal point will be, and all of these gaps here will be zeros. So 1, 2, 3, 4, 5 zeros. So our answer for this would be 0.0000399, and our unit is liters. Okay, next we're going to talk about significant figures. You will hear me calling them sig figs for the majority of the year, just so you are aware. Sig figs are basically used in chemistry to make sure that our data is accurate to the correct value. So when we are determining how many significant figures a number has, there are three important rules to which of those numbers are significant. The first one is all digits that are not zero count as significant figures. So any digit between 1 and 9, that counts as a significant figure. The next one is zeros between two non-zero numbers. So if you have 1001, those two ones are significant, but also since those zeros are between two non-zero numbers, those zeros count as well. So 1001 would be considered 4 total sig figs. The last type of value that is significant are trailing zeros following a decimal. So if you have a decimal point and there are zeros following that decimal point, those are also considered significant. Now, leading zeros are never significant. Those never count as significant figures. And trailing zeros where there is no decimal point do not count as well. So let's do some rounding practice with sig figs. So in this first problem, it said round the following number to 4 sig figs and then express the result in scientific notation. So here we have 34.9827. It says 4 sig figs, so we're going to go ahead and cut this off after 4 sig figs. 2 does not round up, so our new number would be 34.98 grams. Now it also said to express this in scientific notation. Since this is a number larger than 10, we know we're going to have a positive exponent. We do have to move the decimal point one time to the left to get it to a number between 1 and 10, which means we're going to have a positive 1 as an exponent, and then we cannot forget our unit, which is grams. The second one says round the following number to 4 sig figs and also expressed the result in scientific notation. So here it says 4 sig figs. After 4 numbers, I'm going to cut it off here. Since this is not after a decimal point, it is a part of the whole numbers, we are going to just fill in those with zeros. So we have 32,910,000 grams. Again, since this is not a decimal point, this is a whole number, we have to put in those zeros in order to keep the integrity of the number. Because if we just cut it off after that 1, it would be 3,291, which is much different than 32,910,000. Now for putting this in scientific notation, we imagine that decimal point at the end of the number. We have to move it 1, 2, 3, 4, 5, 6, 7 times. So we will have 3.291 times 10 to the 7th because it is a very large number. And then again, we don't want to forget our unit. And then the last one, we have 9.03 plus 0.0045 minus 2.9. According to the order of operations, we want to do the addition first. So we're going to have 9.03 plus 0.0045. Then we're going to subtract 2.9. That is going to give us 6.1345. Now, according to sig fig rules, if you are given multiple values in a question, you're going to go off the sig figs from the smallest value. So in this case, we have 9.03, which is 3 sig figs. We have 0.0045, which is 2 sig figs. And we have 2.9, which is also 2 sig figs. So 2 is the smallest here, so we want our answer to also be in 2 sig figs. If we cut this off after the second significant figure, we do not have to round up. So it will be 6.1 will be your answer. The next thing we're going to talk about are types of chemical reactions. So we have synthesis, which are 2 or more reactants becoming one product. We have decomposition, which is the opposite of synthesis. We have combustion, which is a hydrocarbon and oxygen gas reacting to form carbon dioxide and water. And then we have our replacement reactions. So single replacement will be a compound reacting with an element to form a new element in a new compound. And then for double replacement, we will have two ionic compounds reacting to form two different and new ionic compounds. All right, so now we're going to identify types of chemical reactions. So the first one, we have two ionic compounds reacting to form two new ionic compounds. The reason we know they're ionic compounds is because they are a metal paired with a nonmetal. We have sodium, which is a cation with a positive 1 charge, and calcium, that is also a cation with a positive 2 charge. Then we have bromine, which is an anion of a negative 1 charge, and hydroxide, which also has a negative 1 charge. Now, in a double replacement reaction, which is what this is, you have the cation of the first element bonding to the anion of the other, and vice versa with the other cation. And those will form two new ionic compounds. So this first example would be a double replacement reaction. Next, we have two reactants forming one product, which is the definition of a synthesis reaction. Then we have a hydrocarbon reacting with oxygen gas to form carbon dioxide and water. Combustion is very easy to find and to identify because combustion will always have CO2 and H2O as a product and will always have oxygen gas as a reactant. So this is your telltale sign that this is a combustion reaction. Our next one is the opposite of synthesis. We have one reactant forming two products, which is going to be decomposition. And then the final example is going to be very similar to double replacement. However, we have a single element on each side, so this will be single replacement. All right, so now let's practice balancing some chemical equations. So I personally like to start with the atom on the left and work my way towards the right. If you like to do it a different way, that is totally fine as long as we're getting the same answer. So I'm going to start first off with carbon. I have one carbon on the left and one carbon on the right, so I'm going to move on. I have two sulfurs on the left, one sulfur on the right, so I need to multiply it by 2 in order to get that balanced. And then finally with my oxygens, I have 2 on the left and 2 plus 4 on the right, which is 6. So in order to get my left oxygen to 6, I will need to multiply it by 3. And now I believe I'm done, but I just want to double check. If I look at my carbons first, I have 1 on the left and 1 on the right. My sulfurs, I have 2 on the left and 2 on the right. And for my oxygens, I have 6 on the left and 6 on the right. So everything is balanced. For my next one, it's a little bit trickier. We have a combustion reaction. So I'm going to start off again with my carbon. So I have 1 carbon, 1 carbon. I then have 4 hydrogens and 2 hydrogens. So I'm going to multiply this by 2. And then for my oxygens, I have 1 plus 2 is 3. And I have 4 here. So since I have an odd number on the left, I'm going to go ahead and turn that odd oxygen to an even by multiplying the entire compound by 2. When I do that, that does change my carbons. So I now have to put a 2 in front of CO2. And that does change my hydrogens. So now, since I had a total of 4 here and I multiplied by 2, I now have 8 hydrogens on the left. In order to make this H2 8, I'm going to have to multiply it by 4. And now we can go ahead and go back to the oxygens and see if we made any headway. So on the right now, I have 2 times 2, which is 4 oxygens, plus 4 times 1, which is 4. So I have a total of 8 oxygens on the right, and now I have 2 plus 2, which is 4 oxygens on the left. So in order to make all of those 8 on the left, I'm going to multiply this O2 by 3, which gives me 6 plus 2 is 8. So now that I think that I have our balanced chemical equation, we're going to go ahead and double check that it is balanced. So I'm going to go ahead and rewrite this just so it's a little bit less confusing looking. So if we want to just double check that we have the correct amount of each atom, for our carbons, we have 2 on the left and 2 on the right. For our hydrogens, we have 8 on the left and 8 on the right. And for our oxygens, we have 8 on the left and 8 on the right. So now that everything is balanced, we know that this is our final balanced chemical equation for this combustion reaction. Alright, so now we're going to practice writing out a chemical equation from a word problem and then balancing it from there. So here it says aluminum metal. Aluminum is not diatomic and it is a solid. So there's only one of those. Then we have aqueous. Remember, if it says aqueous, we're going to put AQ next to that compound. Copper 2 chloride. Now these Roman numerals is telling us that copper has a positive 2 charge. And we know that chlorine in group 17 is going to have a negative 1 charge. So when we're writing out that compound, we're going to need 2 chlorines to balance out that copper, and we know it's going to be aqueous. Now, if it did not give us our products, we could definitely figure it out because this is a single replacement reaction. However, it told us that we have aqueous aluminum chloride, so we can go ahead and write that out. We know aluminum is positive 3 because it's in group 13, and chlorine is negative 1, it's in group 17. So when we are writing out that formula, we're going to need 3 chlorines to balance out that aluminum, and we know that it is aqueous, which means dissolved in water. And then finally, solid copper. From here, we can go ahead and balance our chemical equation. Everything is actually one of each except for chlorine. So let's just start at our chlorines. We have 2 on the left and 3 on the right. So we're going to multiply them by the number to get them to 6. So for CuCl2, we're going to multiply that by 3. And for AlCl3, we're going to multiply that by 2. Now that changes our aluminums to 2 on the right. So we're going to put a 2 on the left. And that changes our coppers on the left to 3, so we're going to put a 3 on the right. And now we have a balanced chemical equation. Our next one is aluminum reacts with oxygen to produce aluminum oxide. So aluminum is not diatomic, so we only have one of those. It is a solid. Then we have oxygen, which is diatomic, meaning it needs 2 to be on its own. So it's going to have a subscript of 2 next to it. And we know that oxygen is a gas. And this is a synthesis reaction, so it's forming one product of aluminum oxide. Aluminum has a positive 3 charge. Oxygen has a negative 2 charge. So you're going to need 2 aluminums and 3 oxygens. And aluminum oxide is a solid. So from there, we can go ahead and balance our chemical equation. I'm going to first do the oxygens since there isn't an odd and an even, so we're going to have to multiply both. So the common multiple of 2 and 3 will be 6, so we're going to multiply O2 by 3 to get to 6, and Al2O3 by 2 to get oxygen to 6. Now that we have our oxygens balanced, we can go ahead and make this aluminum on the left 4 so that our aluminums balance as well, and that is the final answer for that problem. Alright, next we're going to work on empirical and molecular formulas. I'm going to save you from just listening to me read this, and if you want to read through these steps, just go ahead and pause it. So if you're anything like me, actually doing a problem is going to help you understand better than reading the directions. So let's go ahead and do a couple examples together. So the first one already gives you grams of iron and oxygen, so you do not have to do step number 1. If those were percentages, you could simply just change those to grams. Now the next piece is to convert our grams to moles, and we use that by dividing the molar mass from our AP chemistry periodic table. So if we have 34.97 grams of iron, in order to get that to moles, we're going to use the conversion factor 1 mole is equal to the molar mass. Now the molar mass on your periodic table is 55.85 grams of iron. And if we take those numbers and divide them, we end up getting 0.626 moles of iron. Now we're going to do that same thing for our 15.03 grams of oxygen. And 1 mole of oxygen, we have 16 grams of oxygen. If we take 15.03 and divide 16, we get 0.939 moles. Now from here, step 3 is to establish our ratio. So for our ratio between Fe and O, we have 0.626 to 0.939. Step 4 is to divide all the numbers by the smallest one. In this case, it is 0.626. From there, we end up getting 1 to 1.5. This is still not whole numbers. So what we're going to do is we're going to divide or multiply that by 2 to get 1.5 to a whole number. That means our final ratio will be 2 to 3. Now that we have our final ratio, we can go ahead and write out our empirical formula. So we have 2 irons and we have 3 oxygens. So Fe2O3 would be your answer for this one. Alright, so this next question gives you the mass of the entire sample. It says that it's only nitrogen and oxygen, and it tells you that 4.2 of that sample is nitrogen. So in order to get the amount of oxygen, we're going to take that 13.8, subtract the 4.2 grams of nitrogen, which will give us 9.6 grams of oxygen. So now that we have the amount for both of our elements that make up the compound, we can go ahead and do step number 2, which is take our grams of each and convert them into moles. So for nitrogen, we're going to divide by the molar mass of nitrogen in order to get it to moles. From your AP Chem periodic table, it is 14.01 grams. That's going to give us 0.2998 moles. For oxygen, we're going to do the same thing. 1 mole over the molar mass in order to get that to moles. When we do that, we get 0.6 moles of oxygen. So remember, now we want to establish our ratio. We have, I'm so sorry, is this supposed to say N? We have N to O at 0.2998 to 0.6. If we divide both of those by 0.2998, we're going to get 1 to 2 ratio. So our empirical formula is going to be NO2. So now that we have our empirical formula, we can go ahead and solve for molecular formula, which are these steps down here. So the first step we're going to do is we're going to find the integer that we're going to place in front of NO2 to find the molecular, and we do that by taking N equals the molar mass of our empirical formula on the bottom. So if we have molar mass of NO2, we're going to have 1 nitrogen at 14.01 plus 2 oxygens at 16. It's going to give us a molar mass of 46.01. So that's going to go on the bottom. And our given mass is going to go on the top, and our given mass was given to us at 90.3. Then that's going to give us our integer. So it ends up being 1.96, which we are going to round to our whole number of 2. Now that we have our integer, we can multiply our integer by our empirical formula. So if we have 2 times NO2, our molecular formula is going to be N2O4. So we now have our molecular formula and our empirical formula. Okay, so next up is limiting reactants. Before we go into the nitty-gritty of limiting reactants, theoretical yield, so on and so forth, I wanted to go over a very basic example of what this means in a chemical reaction. So say you are making hot dogs. In order to make one hot dog, you need one hot dog and one hot dog bun. Now, if your hot dogs and your buns were your reactants and your full hot dog with a bun was your product, there is going to be one of those reactants that limits how many hot dogs you can make. So in this example, we have 5 hot dogs and 4 hot dog buns. Now, from those combinations, we can only make a total of 4 hot dogs. That's because the buns are limiting how many we can make. So in this specific example, our hot dog buns are going to be our limiting reactant because they are limiting the amount we can make. And our hot dogs are going to be our excess reactant because when we do make our product, there's going to be excess of that reactant left over. And finally, the theoretical yield is what is produced by that limiting reactant. So in this case, our 4 hot dogs that were made are our theoretical yield. Okay, so now let's go back to real chemistry. So if you are unsure about limiting reactants at this point, why don't you stop the video and read through the directions on the left. Now in this specific question, it's telling us that 2.8 grams of solid aluminum is reacting with 4.15 grams of chlorine gas. It's asking us to find the theoretical yield of aluminum chloride. So the first step, in my opinion, is to create the chemical reaction. So we have solid aluminum. Aluminum is not diatomic, so there's only one. And then we have chlorine gas. Chlorine is diatomic, so there are 2 of them. Then we have aluminum chloride as the product. So aluminum is a positive 3 charge, chlorine is a negative 1. So we're going to need 3 chlorines to balance that out. Now, in order to balance out the equation, let's look at those chlorines. So we have 2 and 3. So our common multiple is going to be 6. So we need to multiply this one by 3, this one by 2, which changes our aluminums to 2. And now we have a balanced chemical equation. Now that we have a balanced chemical equation, we can go ahead and convert our amount of reactants into moles of our product. So we are given 2.8 grams of aluminum and 4.15 grams of chlorine gas. Now we're going to first convert these into moles by using the molar mass. The molar mass of aluminum from your AP Chemistry periodic table is 26.98 grams. And our molar mass of chlorine is 35.45 times 2, which is 70.9. And then finally, we're just going to go to moles since it did not ask specifically for mass. And we want to put the moles of our product on top. And we want to cancel out our moles of reactant on the bottom. So we have 2 moles of aluminum from our balanced chemical equation and 3 moles of chlorine gas from our balanced chemical equation. So if we solve for the top equations, we end up getting 0.104 moles of aluminum chloride. And if we solve the bottom, we get 0.039 moles of aluminum chloride. So next step is to select the smaller one. In this case, the smaller one is 0.039. This will be labeled as our theoretical yield. Then we have whatever produced the theoretical yield would be our limiting reactant. So chlorine gas is our limiting reactant. And all other reactants would be excess reactants. In this case, there's only one, which is aluminum. Okay, so this question is a multi-layered question. The first thing I'm going to do personally is to create the chemical reaction. So we know that barium chloride, BaCl2, is reacting with AgNO3. And we know that this is two ionic compounds, so it's going to be a double replacement reaction. So barium is going to go with nitrate. Barium's a positive 2, so we're going to need 2 nitrates to balance that out. And then we're going to have silver chloride, AgCl. So now we want to balance that chemical equation, so the bariums are good, the chlorines are not, so we're going to put a 2 in front of AgCl, and then we're going to put a 2 in front of AgNO3, and then it's balanced. So from here, we can go ahead and start solving. However, we're not given the direct amount of our reactants. We know for a fact that AgNO3 is our excess reactant, so we do not have to solve for that. We can go ahead and just solve for our limiting reactant, which is BaCl2. So we're not directly given the amount in grams, however, we are given molarity. Remember, molarity is moles of solute over liters of solution. And we're trying to find this moles of solute. So if we're trying to find moles, we're going to have to multiply molarity and liters. We have molarity at 0.314, and we also have liters at 0.025. So if we do that, we end up getting 0.00785 moles of barium chloride, which means now that we have our moles, we can go ahead and convert into grams of our product AgCl, which is what it's asking for. So now that we're in moles, we can go ahead and do the mole ratio. From our balanced chemical equation, we have 1 mole of BaCl2. We're trying to get to AgCl, and we have 2 moles of that from our balanced chemical equation. Now we can go to grams by multiplying by the molar mass. We know from our periodic table, we can just add the molar mass of Ag and Cl, and you get 143.32. When we multiply 143.32 times 2 times 0.00785, we get 2.25 grams of AgCl. This is our theoretical yield. Now that we have our theoretical yield, we can go ahead and plug everything into percent yield. So for our percent yield, we're going to have actual, which is given to us at 1.82 grams, over theoretical, which is 2.25 grams, times 100. And that's going to give us a theoretical yield, or sorry, a percent yield of 80.9. And that is our final answer. Okay, lastly, we are going to go over a few very important items about memorization this summer. The first thing I want to go over are the states of matter of our elements on our periodic table. So the first thing I want to go over is that all metals are solid except mercury, which is a liquid at room temperature. Then we have our metalloids, which are all solids. Then you should know that carbon, phosphorus, sulfur, and selenium are solids. Bromine is a liquid. And then all other nonmetals are going to be gases. There are several elements that you need to memorize the element name and the element symbol before you come to AP Chemistry on the first day of school in August. I wanted to give you a visual representation of all of these elements, so if you want to pause your screen and take a screenshot of that, I think that this might be very helpful for you. In the very last part of this video is just going to be a brief overview using the periodic table. So a few things I want to go over before we begin marking up this periodic table. One is ionic bonding. Remember, ionic bonding is a metal and a nonmetal, and covalent bonding is a nonmetal and a nonmetal. So the metals are on the left side of your periodic table, the nonmetals are on the right side of your periodic table. So before we go into which elements make ionic and covalent bonds, let's go ahead and mark up our periodic table. So the first thing I want to go over is valence electrons. So everything for valence electrons, we're going to go ahead and put in purple. Group 1 valence electrons, they only have one. So when they form an ion, they have one electron in their outermost shell. Do you think that they're trying to obtain 7 more, or do you think they're just going to get rid of that one and go to the previous sublevel? The answer is the latter, so they're much more likely to just get rid of one. So that means they're going to have one extra proton, which is why group 1 elements form a positive 1 charge. So all charges are going to be in red. Now our group 2 elements have 2 valence electrons, and it's going to be the same process on why they want to give away those 2 rather than bring on 6 more. But they're going to have 2 extra protons, which is why when they have an ion, they form a positive 2 charge. We're going to kind of skip over the transition metals for now, just for sake of clarity, and go over to group 13. Group 13 elements have 3 valence electrons. They're going to more likely get rid of those 3 valence electrons or donate them to another atom, and they're going to have a positive 3 charge because of that. Now our group 14 elements are more likely to share their valence electrons, so they're going to covalently bond. So we're just going to skip over that for charges for now. Then we go to group 15, which has 5 valence electrons. Now they have 5, so in order to get 8, they only need 3 more. So they're going to be much more likely to have or accept 3 electrons, which is going to give them a negative 3 charge because electrons are negatively charged. Then we go to group 16, which has 6 valence electrons. They're going to obtain 2 more, which gives them a negative 2 charge when they become an ion. And then we have our group 17 elements, which have 7 valence electrons. So they only need 1 more electron to be stable. So when they form an ion, they're only going to have a negative 1 charge. Then we have our group 18 elements, the noble gases, which are the most stable on the periodic table because they already have a full octet or 8 valence electrons. So these are the number of valence electrons circled in purple, and then our charges if they were to form ions that are written in red. Now let's talk a little bit about covalent bonding. So we're going to go ahead and start in group 14 with our nonmetal of carbon. Remember, covalent has to be nonmetals and nonmetals. So we're going to start in group 14 with carbon. Carbon has 4 valence electrons, so when we draw its dot structure, it's going to look like this. Now, as you can see, there are no lone pairs on here. They are all single electrons. So carbon is going to form 4 bonds. Now, they don't have to form 4 single bonds. It can be 2 double bonds, a double bond and 2 single bonds, a triple bond and a single bond. It doesn't matter, but carbon wants to form 4 bonds. Now, nitrogen in group 15, and this can be any group 15 nonmetal, not nitrogen, it's just my example. Every element in group 15 has 5 valence electrons. So if you draw the dot structure, we have 1, 2, 3, 4, 5, which means these group 15 elements will have 1 lone pair and want to form 3 bonds. So we're going to go ahead and put 3 bonds, 1 lone pair. Now again, this can be 3 single bonds, it can be a double bond and a single bond, or it can be a triple bond. It doesn't matter as long as it's those 3 bonds. And there are exceptions to these, but we're just going over general rules right now. Then group 16 have 6 valence electrons. So if we're using oxygen as an example, 1, 2, 3, 4, 5, 6, which means they will have 2 lone pairs and want to form 2 bonds. So I'm going to put 2B for 2 bonds and 2LP for 2 lone pairs. And then finally, our group 17 elements, we'll use fluorine as an example. 1, 2, 3, 4, 5, 6, 7 will form 3 lone pairs and only need 1 bond. So these will have 1 bond, 3 lone pairs. Alright, so I hope this video helped you out with your summer homework and any questions you might have had from general chemistry. If you have any questions beyond what has been gone over in the video, I urge you to look online for some videos that cover what you're specifically needing. If not, you can always come to class on the first day of school with a list of questions, and I'm happy to get to them by the end of the week. I hope you have a great rest of your summer, and thank you so much for watching this and getting ahead for our class. Bye!